So here's the worked solution for our recent homework, projectile motion question 3 from the 2018 mechanics exam. So a water balloon is launched covering a horizontal distance of 21 meters and it's in the air for 2.8 seconds. A asks us to calculate the horizontal velocity of the balloon. So T is 2.80 seconds. DH is 21.0 meters and VH is our unknown, and we should be able to use the formula VH equals DH over T, giving us 21.0 divided by 2.80, which comes out as 7.5 meters per second. For B, we're asked to show that the initial velocity of the water balloon is 15.6 meters per second, and note in the question that that's shown as the diagonal, so we're trying to find a diagonal. So the things that we know is that T is 2.80 seconds. We know that A is negative 9.8 meters per second squared. The initial vertical velocity is what we are trying to find at first, because we can piece this together. We know the horizontal velocity, which is 7.5 meters per second, and we know that there's going to be a vertical component, and that is what we're trying to find. So that's our VVI. And then if we can get this, we can use Pythagoras to put it together to find the VI, the initial velocity. So this is the initial vertical velocity here. And we know that halfway through the flight at the apex, so at apex T is half, so 1.40, and the final velocity, if we're considering that portion of the flight, would be 0. And so we can use the formula VI or VVI is equal to VF minus AT, and we got that from rearranging VF equals VVI plus AT. You'll see that written as VI. I've just used VVI to try and keep the vertical component distinct from the diagonal component. Okay, so then substituting into this formula here, we've got VVI is equal to 0 minus 9.8 times 1.4, and that comes out as 13.72 meters per second. I'm not rounding that at this stage because it's an intermediate part of my answer. So then coming back over to our triangle, we know that this side of the triangle is 13.72, and so we can use Pythagoras. So VI squared, hypotenuse, is equal to 13.72 squared plus 7.5 squared. That becomes VI is equal to the square root of 13.72 squared plus 7.5 squared. Put that in brackets, do my square root over the whole thing, and that should come out at 15.6 meters per second. Normally, if the question asked me about the initial velocity and it was looking for the diagonal, I would be looking to give a value for the angle as well. But because it's a show question and it was only asking about the value of the velocity here, I'm not worried about the direction in this case. So for part C, if the same water balloon was launched at the same initial velocity on planet X, where the acceleration due to gravity was 3.7 meters per second squared downwards, would the water balloon go the same horizontal distance? Clearly explain your answer. And so what I would state here is if acceleration became negative 3.7 meters per second squared, which is lower than negative 9.8. So it's a smaller value for acceleration than we're used to. Then the balloon would spend longer in the air. As VI is constant or remains unchanged. So what we're saying there is that T increases as VH also remains constant. I hope you guys can read my writing here. And T increases, DH will also increase. And I might put in brackets there that the formula I'm using for that one is DH equals VH times T. So with T increasing and VH staying the same, DH is going to increase. And it's always a good idea to state the formula that you're using or referring to in those questions. Okay, so in part D, we're back on Earth and Jimmy is going to try and catch the water balloon. He's 12.5 meters from the launch position, so our DH is 12.5 meters, and his hands are 1.1 meters above the top of the launcher. The water balloon is launched at an angle of 35 degrees to the horizontal. It might be a good idea for you to draw a diagram to help you understand what's going on here. And we're told that the horizontal component of the velocity is 10 meters per second. So what we've got going on in terms of the vector diagram for the velocity is we've got a diagonal like this with an angle of 35 degrees in here, and we are told that the horizontal component is 10.0 meters per second. We're being asked to find by first showing that the vertical component of velocity is 7 meters per second. So that's our velocity vertical initial, which is our first unknown in this question. We know that A is negative 9.8, and what we're going to do here is use a bit of trigonometry to get VI. So we've got from the 35, we've got the adjacent, we don't know the opposite, so we're going to be using tan. So tan of 35 degrees is equal to opposite over adjacent, so that's VVI over 10.0. That becomes VVI is equal to 10.0 times tan 35, and that's going to come out at just over 7 meters per second. So that's the first step in the question. The second part is a little bit more complex. Determine if the water balloon will arrive at the right position for Jimmy to catch it. In order for him to catch it, it has to have covered a horizontal distance of 12.5 meters at the same time as being a vertical height above its launch position of 1.1 meters. So what we can do here is we can work out the time that it would have taken to cover 12.5 meters, and then use that time value in one of the other kinematic equations to work out its vertical distance. So I'll jot that down here. To catch, DH must be 12.5 meters, and dV must be 1.1 meters at the same time. So time is going to be quite important for this. So first off, we can work out the time that it's going to take to cover the horizontal distance of 12.5 meters. So T is equal to dH divided by VH, so that's just D over V, which is 12.5 meters divided by 10 meters per second, which comes out at 1.25 seconds. Now we can take that value for time and we can substitute it into another equation, a kinematic equation. So if we were interested in the vertical distance, then we could say that dV is equal to VVI times T plus half AT squared. Okay, and so that gives us, the VVI was 7 times 1.25 seconds plus half of negative 9.8 is minus 4.9 times 1.25 squared. And when we crunch those numbers, we get something like 1.09, I think it's like 35 or something. Sorry, 375. And that's in meters. And so what we can see there is that at the time that it's covered 12.5 meters horizontally, it is at a height above its launch position of 1.09375 meters. Okay, so it's effectively like 6 centimeters below where his hand would be to catch it. So assuming that he can move his hands a little bit, he would be able to catch that no problem. Alright, and so that's the worked solution there. Hope that's helpful to you. I'd like you to check your answers, and then if there's anything that you don't understand, you know, if you haven't got it right and you're not sure why, then let me know either through Stream or in a private comment on the assignment if you're not comfortable asking out in front of everybody else. But I've really appreciated you guys discussing things on Stream. Makes my life a lot easier, and it's great to see you guys helping each other out. Alright, keep up the good work, boys. Thank you.